record the conversation that we have and so on, and post it in the class website as well. Um, so anybody's done with this problem, at least finding out the final pressure? You good? Thank you. Have you calculated the change in the internal energy? Not yet? Okay. You would need to use essentially all the information that you have. Let's see. This is on. That's on. That's on. All right. So we'll do this together as well, just as a review. We have a container of a constant volume, and we simply heat it up. We put it on a stove, or a Bunsen burner, or a hot plate, depending on what you're looking at. And then it changes temperature from 25 degrees Celsius all the way to 100 degrees Celsius. And I know that the initial pressure is 1.5 atm. The initial temperature is 25, and the volume is a fixed volume of 10 liter. At the end state, after I heat it up, the final pressure is something that I want to solve. The final temperature is going to be 100 degrees Celsius, and the volume, because it's fixed, is equal to 10 liter. I'm assuming, of course, because the container is fixed and the volume is capped, so that the number of moles before and after is the same. Right. All right. So let's try to solve the first question first. So what is the final pressure in this system? Well, we can use the equation for ideal gas changing conditions. So P1 V1 over N1 T1 equals to P2 V2 over N2 T2. Yep, it's showing it perfectly fine on the screen. And I know I'm going to cross off some information to make it a bit easier. I know the volume before and after is the same, so I can cross it off. And I also know that the number of moles is going to be the same because the container is fixed. It's not open to the atmosphere. So the equation becomes easier. That is, this has become P1 over T1 equals to P2 over T2. So that's kind of the extent for the ideal gas law. We simply now have to put in the information that we want. We want to find out P2. So let me just put in the information actually. So I know the initial pressure is 1.5 atm. The initial temperature is 25 degrees Celsius, but remember, whenever we're talking about ideal gas law, we always want to change it to Kelvin scale. And this is P2 divided by the final temperature is 100 degrees Celsius. Again, turn it into Kelvin, plus 273. And that's what we have. All right, so let's calculate the final pressure here. We simply have to divide 1.5 with 298 and then multiply by 373. And we should find in the end, multiply by 373, yeah. So we should find P2 in the end to be 1.8775 atm. I'm not a stickler for sig figs. As long as you keep things in terms of 3-ish, that's good enough for me. I'm not sure what happens here, but I may have to get a new coffee maker because this is not dripping properly. Anyway, yeah, ow, it shouldn't be doing that. But we're just going to wait. At some point, it is. There's enough water. Somehow the line seems to be clogged and it just won't drain the water out. Anyway, so that's the final pressure. Josh, would you mind just unplugging it or turn it off actually? Yeah, there should be an off button there. Thank you. All right, so that's the final pressure. Now, that's one of the questions. So what is the final pressure? What is delta U? What is W and Q? So we've already figured out the final pressure. So in order to find out the change in the internal energy, the equation that we want to know is this is just equal to the number of moles times the heat capacity at a constant volume times the change in temperature. And earlier I mentioned that the gas itself is just a monatomic ideal gas. We don't really care what kind. It could be argon, helium, and so on. So if we know that information, we know that the CV is going to be equals to 3 over 2 R. And the 3 over 2 comes from the gas moving in 3 dimensions, and each of the dimension in which it moves carries 1 over 2 R amount of heat capacity. And we know the change in temperature is just 100 degrees Celsius, my final temperature, minus the initial temperature. And the initial temperature is just 25 degrees Celsius. And remember, whenever you're looking for the change in temperature in Kelvin and then the change in temperature in Celsius are basically the same thing, because you add 273 and then you subtract out 273. Now the question is, what is the number of moles that I have? So this is the information that I'm still missing, but I can use the ideal gas law, PV equals to nRT. So the number of moles is simply equals to the pressure times volume divided by RT. Okay. Anybody gotten to here? Yeah? Question? No, you keep it the same way too. So the final temperature is 25 and then the initial is 100. So what happens is that the change in the internal energy would be a negative number, means that it loses when the gas becomes colder, the energy goes down, so the change is negative. So the equation remains the same whether you're going to hotter or colder. The sign tells you whether it's losing energy or gaining energy. Okay, so let's do this number. I can choose, we've already figured out the final temperature, volume, and so on. But it's an ideal gas law, and our assumption is the number of moles constant. So either way, either of the information that we use, we should still get the same number of moles. So I'm just going to use the first information. So this is 1.5 ATM times the volume is 10 liter divided by the ideal gas constant. Oh, I forgot to write it down on the board. 0.08206. Oh, 06, I'm missing a number there. ATM liter per mole Kelvin times the temperature, and I choose my initial temperature to be 25 degrees Celsius, so this is the 298 Kelvin. It's just the 25 plus 273 is 298 Kelvin. Okay, so let's just kind of plug in the number here to figure out the number of moles. 5 times 10 divided by 8206 and divided by 298. We should get in the end the number of moles to be 0.6134 mole. Okay, so that's the number of moles. Alright, now that we figure out the number of moles from ideal gas law, we can put it back in to the equation for the change in the internal energy. So far so good? Yeah? It becomes more confusing simply because we're adding multiple concepts together. Times 3 over 2 R times 75 degrees Celsius. So what unit of R do I want to use in this case? Well, in the previous example, when I'm trying to find out the number of moles, the information that I have is in terms of ATM and liter. So the unit of R that I'm going to use also is going to be the one that have ATM and liters in it. That way we don't have to do any more unit conversion. Here, I'm trying to figure out the internal energy, or I should say the change in the internal energy. So the unit that I want in the end is in joules. So instead of using the 0.08206, I'm going to use the 8.3145 joules per mole Kelvin, because that's just easier. Actually, the mole Kelvin or mole Celsius is also the same thing, but and the change in temperature in Celsius and Kelvin is also the same thing. So I'm kind of being hand wavy here, and then just cancels out the unit. The rest is just putting all the numbers in the calculation. just kind of make sure that you're using the proper value of R. Okay, 0.6134 times 1.5 times 8.3145 times 75. So in the end we have, let me try to cancel all the units while we're at it. Mole cancels out, Kelvin cancels out, so the only units that we have left is in joule. So the change in the internal energy that we calculated is going to be 573.8 joules. Okay. What else? Okay, so that's kind of about the second portion. Now finding W and Q requires a bit more visualization that we haven't. You could kind of figure it out. But it just takes a bit more imagination, and I haven't explicitly mentioned it yet. So the system that we're working on is that we simply heat up the gas at a constant volume. We fix the volume, right? So in order to go from 25 degrees Celsius to 100, all I did is just put it on the stove. So if I were to do this, what is the amount of, I already know the amount of internal energy. That was the 573.8 joules. So what is the amount of work that I perform in this particular process? 0, thank you. So I didn't do anything. All I did is just put it on the stove. And you can also see that there's no work being done, that is, nothing is moving. Nothing is moving. Therefore, the work that we perform is 0. And therefore, if I want to find out the number Q, I have to use the information about the change in internal energy. Delta U is equal to Q plus W. And I know that W is 0, so that crosses out. Okay. So delta U equals to Q, but this is only true at a constant volume, and therefore the amount of heat that I need to put in, so the amount of heat that I need to put in Q must be equals to delta U, which is 573.8 joules. Okay. So far so good? Yeah? What up?
So the work is 0 because it's not moving?
Right. If I simply put something on my stove, on my pot on the stove, then I'm not doing any work, because all I did it's so if I were to stir the water really a lot, and then if you shake the water a lot, if you just have water bottle, then that's what we're performing is work, because water is moving up and down and so on, right? But here all we did is just put it on the stove, so no work is being performed in this case. Yes, no work is being done. So we separate out, we distinctly splice off the definition of heat versus work. So heat is when temperature is being, energy is being exchanged when something is hotter. In this case, the flame is hotter. Whereas work is when you physically move something to increase its energy. Yeah. I'll get to you in a bit. Yeah.
Dependent on pressure and volume. If any pressure or any volume changes, can we see that in this way?
Only if the volume is changing. So even if the pressure is changing in this thing, right? Yeah. So we start up from 1.5 to 1.8.
Okay, but it's just like if the pressure changes, it would just be still vertical.
Yeah. Okay. Yeah. Yeah. So we didn't go into that much details in this, but yeah.
Only if the volume changes, then you see mechanical work.
Yep.
Okay. Yeah. Totally.
That's the same thing. Okay. So only if the volume is changing that the mechanical work is actually happening. Okay, so that's one example that we have. Now, if I were to do the same problem, or very similar problem, and instead of doing this process at a constant volume, I actually perform this process at a constant pressure. Okay. So I still heat up my gas, but instead of heating it at a constant volume, I heat it up at a constant pressure. That is, in order to achieve that constant pressure, all I have to do is just put a lid on it. Instead of fixing the lid in one side so it doesn't move, I simply put a weight on it, like put something heavy on top of it to make sure that the pressure is the same. That as the gas is being heated, when you heat up a gas, if you let it heat up at a constant pressure, the volume is going to expand, right? And in the end, you get essentially an expansion in the volume. We can also use the same equation that we did before, which is P1 V1 over N1 T1 to find out the final volume. But that's not what I'm going to try to ask. Now, if my gas here changes from 25 degrees Celsius to 100 degrees Celsius, what is the change in the internal energy in this particular case? Nope. It should be the same. It should be 573.8 joules, the same as it was before. Because, again, the internal energy is just the kinetic energy of the molecules that we're looking at. So here, the molecule is moving at 25 degrees Celsius. It really doesn't matter that it's at 100 degrees Celsius, whether it's a constant pressure or a constant volume. All the molecule knows is that it's now moving at this higher kinetic energy at 100 degrees Celsius. So the delta U, whether we're talking about the system at a constant volume or a constant pressure, the change in the internal energy is the same, because what we're interested in is the change in temperature. That is, the change in temperature is the same before and after. Therefore, the molecule is not smart enough to know whether it's moving at a constant pressure or volume. It just knows it moves faster now. And as long as the temperature is the same, they have the same amount of internal energy.
Can you say the amount of internal energy is just distributed differently among Q and W in this case? So like some of it went into kinetic energy?
Yes-ish, kind of. I don't actually, the answer is yes, but we'll get to that in a bit, I think, hopefully. Are you okay with that? It's the concept.
I get the concept, I just don't think that internal energy should be using that formula because it can include CV, and CV is not this case because it's not a constant volume.
So, hence the problem that we're trying to tackle today. You see, the change in the internal energy. So before I go into there, do you guys get my point that the internal energy is the same? The gas, both, whether constant volume or constant pressure, the gas are having exactly the same temperature. So they must move at exactly the same speed, spin the same way, and so on. It really doesn't matter. The gas doesn't care that it lives in a constant pressure or volume. All it knows, it moves in a faster speed, and they move exactly the same temperature. So far, if you guys are okay with that, the definition that I kind of want to kind of put in here for now is that the change in the internal energy at a constant V, based on the math that we just did over here, is equals to the volume. Is equals to the amount of heat exchange. Right, so that's kind of the important thing to get. The change of the internal energy at a constant volume is equal to the amount of heat that we put in. But here, if I were to ask you the same question we did before, what is W and Q? Can you say here that W equals to 0? No, because in order for this gas to expand, I literally have to lift up this weight that I put on top of the lid in order to expand. So in fact here, the work is not going to be 0, it's going to be a positive value. I'm not going to go into the details of it, but the amount of work that is actually going to be performed, actually, the work is going to be a negative value because the gas is expanding, so it's doing work, so it's losing energy because it's pushing against the thing.
So
Sorry.
would it be negative pressure
Yeah.
change in volume? Or P change, yeah.
Right. So I'm actually not going to go into this much details in terms of the calculations. I just wanted to have a sense of whether the work is positive or negative and so on. But in this case, the amount of work that we perform is actually equals to negative P. The pressure is constant times the change in volume here. That's the change in our volume.
Sorry, so the work is negative because the gas had to expend energy.
Yeah. To push, in order for the gas to expand, it has to push against this piston, so it's expanding energy.
And if you push down on the lid,
It'll be positive.
you're adding energy in.
Yep. So if I were to push a gas or a tank of gas to make it smaller, then the work is positive. But if the gas is expanding on its own, you have to push against the external pressure, which is the atmospheric pressure in this case, then the work is negative. You're expanding energy or you're getting energy from this mechanical work. Now, the equation for Q is still the same thing. It's just delta U minus work. Right? So that's kind of the rearranging. So we have delta U is equals to Q plus W. So here, to get Q, which is the amount of heat, which hopefully kind of addressed a little bit of your answer, that in this case, NCV delta T minus a negative number, so it becomes actually a positive P delta V. This happens at a constant pressure. Yeah. My point that I'm trying to get to here is that the amount of heat that I have to put in, so if all I have to do is just put it on a stove, I have to put in more heat to increase the temperature of the gas compared to if we were looking at it at a constant volume. Because not only that I have to make the molecule move faster, I also have to push against the container surface so it expands. So I have to put more heat specifically compared to if my process occurs at a constant volume. So far so good?
And the extra heat went into pushing the lid up.
Yep. The extra heat that we put in simply gets into pushing the lid up. So that's just kind of the basics of it. While the concept of internal energy is easy to understand, it's just the movement of the atoms and so on. That's how fast it's moving. But the problem is that we don't live in a constant volume. And therefore, the amount of heat that we have to put into the system, say heating up this room, we have to take into account the expansion of the gases when we try to cool down this room or heat it up in the winter. So that's going to be a pain in the ass. So instead, around the 16th century, people figure out, okay, I can actually make another equation that takes into account the changes for the fact that gases expands and so on. And essentially that equation is called the enthalpy H. And in order to incorporate for the fact that gases expands, contract, and so on, the definition of enthalpy, this is enthalpy, is equals to the internal energy plus PV. So that's kind of the definition of enthalpy. The enthalpy is equals to the internal energy plus the pressure times volume. So essentially it is really just made up to take into account for the fact that we live in a constant pressure, such that, because what we're interested in this whole thermodynamic is heat and work, we make this to be the case such that the amount of heat exchange at a constant pressure is equals to delta H. So we made it up so that delta H is equals to the amount of heat exchange. And that way, if we figure out what is the delta H and delta Q and so on, if we can tabulate some value at a constant pressure, then we can still get the amount of heat. And we also define this to be N times Cp delta T. and the P here is constant pressure. So specific heat capacity at a constant pressure. So that's the P instead of CV. So now instead of tabulating things in terms of CV, we're putting things in terms of CP. It really is just a made up quantity. Okay, so if I have heating, some kind of heating or cooling system, it's N, the number of materials that I have, times the specific heat capacity at a constant pressure, times delta T. It's purely kind of, we'll make up this new equation in order to make the amount of heat that we're going to calculate a bit easier. And that really is what enthalpy is. And again, the physical meaning of delta H or enthalpy, if you've taken high school chemistry, delta H is equals to the amount of heat exchange at a constant pressure. But it's only true at a constant pressure, and that's about it. It's quite restrictive that delta H is heat exchange only at a constant pressure. So which brings me to kind of another table that I want you to complete. Do I have it here? Let me check. Okay, which brings us to page 24. Right, that's kind of exactly where we are at. We're page 24. And I'm going to make a distinction between gases, solids, and liquid. That is, I'm not going to derive the equations. Before, we've collected values of CV. For a monoatomic gas, this was 3/2R. But the problem is that gases, as we did before, expands by quite a lot. If you increase the temperature of a gas twice the amount, then it's going to expand twice the amount of volume. So what happens is that if the process occurs at a constant pressure, this value of Cp, the amount of heat, or the relative ratio of the amount of heat that we have to put in, is actually going to be higher compared to Cv. That is, but specifically, it's going to be higher by a value of exactly R. Such that is my Cv is 3/2R. The heat capacity at a constant volume, constant pressure is going to be 5/2R. And most of the time, this is what we're going to focus on constant pressure. But we can't go into constant pressure without understanding the molecules itself and so on. So if I have a diatomic gas that can move in 3 dimensions, and also spin around, in this case, I know that my CV was 5/2R, or is 5/2R. But if I want to heat up this gas at a constant pressure instead of a constant volume, the Cp is going to be 7/2R. Okay. And this happens, these are gases, because Cp is greater than Cv because gas expand.
Are you saying that it's allowed more freedom of movement when it expands like that?
Nope. The extra term here, when it expands, it has to push against the container or whatever external pressure. So we have to put in more heat into our system. So that's the extra energy. The extra energy literally goes into pushing the container upward because it's expanding at a constant pressure. If the external pressure is 0, like in vacuum, then it's actually going to be the same, but we're not going to get to that. If you're taking physical chemistry or actually physics courses, you may see that a bit more, but not in our class. We're going to simplify it to just the condition where we live in. We just live in a system of constant pressure. So for metal, this is my solid metal. The Cv was 3/2R, I should say. Yeah, so the value of Cv is 3R, which comes from the fact that they vibrate in 3 dimensions, and each of the vibration carries with it 1 R amount of specific heat. So my guess, that's what I want you to ask you. What is the Cp going to be for solid metal? They're going to be the same because if you heat up some metal, your pots and pan doesn't expand to twice the amount of its volume just because you put it on a stove. The volume remains the same for solid metal, whether you heat it up by quite a lot. So the heat capacity Cp is also going to be the same. It's actually going to be slightly higher because the metal does in fact expand, but the expansion of, say, solids most of the time is about 1/1,000,000th of its initial volume per degree Kelvin. So it's quite negligible. So most of the time, we're just going to assume that they're equal. If you're an engineer and you work, say, building rockets, that's kind of when you want to take into account so that when your rocket goes to outer space, things doesn't shrink and then your bolts and such start to crumble. But otherwise, we'll live more or less about the constant condition, so we don't care about those tiny changes. Oops, I lost my page. Where was I? I think it's supposed to be upward. Okay, and the last one that we did is we have solids, and let's look at liquid water, just H2O. We've already said that the heat capacity Cv is equal to 9R, and the same thing too with water, or actually liquid in general. The Cp is going to be also the same because the volume doesn't change. So as long as your thing, whatever object that you're looking at, doesn't expand and then contract in large quantities, then Cv and Cp are basically the same thing. The only thing that we have to concern ourselves with are mostly just the gases, because gases expands quite a bit, which essentially is where we are. We're on page 24. For ideal gases, Cp is equal to Cv plus R, so just add by 1R. And for most solids and liquid, Cp and Cv are exactly the same thing. Okay. The rest, the calculation, and whatever calculation that you did from last time is going to be the same, right? Except of looking at Cv, you're going to be looking at Cp for the most of the rest of the class. And the distinction between Cp and Cv is that they're different because one of them takes into account expansion, whereas the other one is a constant volume. And whenever your object expands, it have to push against the external pressure, which is case external atmosphere that we have. So the value is going to be higher. Actually, any questions so far before we go on? Yeah. Whatever equation that you did last time is pretty much the same. You're just changing Cv with Cp in this case. So let me move on to the next portion. Actually, let's take a break for a bit, and I'll come back to topic number 4, which is state function. Take a break, get some snacks and so on. I'll figure out what happens with the coffee cup. We'll be back in, this is 10:45, so let's give it a 5-minute break. All right.